In this lesson, we're going to combine the skills we've learned in identifying types of chemical reactions and balancing equations. To start, let's look at this chart where I've made a way for you to approach problems that are asking you to predict the products. Typically, when you're asked to predict products, you will be given the reactants. I've given you a set of things that you can look for to help you decide what type of reaction it is. It's similar to the chart we used for identifying the types of reactions, but now we're just looking at the reactants themselves and then figuring out how do we know what products will come from that. Anytime you see a metal plus a nonmetal, you're typically going to look for a synthesis reaction. Remember that synthesis is combining. And so what we're going to do is take this metal and nonmetal and make an ionic compound or an ionic crystal. To write the ionic crystal, we need to use the rules for writing ionic formulas, and we'll review that in just a moment. As a quick reminder, you'll need to balance the charges for those ions in order to decide what the ionic formula of that synthesis reaction product would be. If you find a single ionic compound, for example, we have mercury here bonded to oxygen. Mercury is a transition metal. Oxygen is a nonmetal, so this is going to be an ionic compound. You can assume that you're going to be asked to write a decomposition reaction. In this case, you'll just write the elements separately because remember that decomposition is just coming apart or breaking apart into its individual elements. Just make sure that you watch out for those diatomic gases or diatomic free elements, and we will look at those in a moment. Next, if you have a metal and an ionic compound, or a halogen and an ionic compound, then you're going to do a single replacement reaction, and you're either going to replace the metal, as in this case. So in this case, you would have the metal zinc replace the metal copper in this ionic compound. Or if we had an example of a halogen, you would replace the halogen. In this case, or you would replace the anion, I should say. And in this case, the anion is this polyatomic ion sulfate. And so if we instead of zinc, if we had a halogen like chlorine, for example, then you would create the chloride ion and rewrite the formula using the chloride ion and leave the sulfate ion out by itself. So for a single replacement reaction, you're going to switch the metals or halogens, depending on what you're given, using the rules for writing ionic formulas. In this case, we have copper and zinc. They both have the same charge, and so it's a breeze to just switch them out for the formula. You don't have to do anything else. If you have two ionic compounds or hydrogen bonded to a nonmetal, then you're going to do a double replacement reaction. You'll need to switch the metals, or the hydrogen in the metal, using the rules for writing ionic formulas. One of the products is going to be a precipitate, which is just a solid that comes out from a solution that is not soluble, meaning you can't dissolve it. It's going to be an insoluble gas or water. So here, if we switch copper and hydrogen, we end up with HCl and copper sulfide. If you have a hydrocarbon, which is a compound made of carbon and hydrogen, and actually you can also do this with compounds that are made of carbon, hydrogen, and oxygen gas as your reactants, this is a combustion reaction. This one's pretty easy. It's hard to identify sometimes, but it's pretty easy to predict the product because the products will always be carbon dioxide and water. To predict products, you're going to use the chart in the previous slide that we just reviewed to predict what the products are even going to be, right? So you'll need to figure out what type of chemical reaction you're looking at and what the products will be. You'll need to write the reactants, your reaction arrow, and the products, making sure that you're taking into account the 7 diatomic free elements that are always written as a molecule with 2 atoms rather than by themselves. And then you'll need to balance the equation. In single replacement reactions, you may be asked to identify if a reaction will even occur. The way you decide that is you have to look at the activity series that is in your chemistry reference tables. Let me bring those over here, right here. When you're looking at the activity series, the higher up it is on the list, the more reactive it is. So for example, if we look at our activity series of halogens, we see that fluorine is the most reactive and iodine is the least reactive. If we look at the activity series of metals, we see that lithium is the most reactive and gold is the least reactive. When you are more reactive, it means that you're more likely to form an intramolecular bond. Remember that that's a covalent, ionic, or metallic bond. So a single replacement reaction will occur so that the more reactive metal is bonded to the halogen on the product side, or if you're dealing with switching the halogens out, it'll be so that the more reactive halogen is bonded to the metal on the product side. Basically, if the more reactive element is already bonded, meaning if it's already bonded in the reactants, no reaction will occur. You need to use the activity series in the chemistry reference tables to know which element is more reactive. Here is a chart to remind you of the charges of ions. The easy ones are groups 1, 2, and then our nonmetals, because they always form ions with the same charge. Group 1 elements will always form ions with a +1 charge. Group 2 elements will always form ions with a +2 charge. Transition metals generally can form multiple types of ions. They can form ions with different charges. The exceptions to that rule are silver, cadmium, and zinc. And so we have those charges right here. So zinc and cadmium will always form an ion with a +2 charge. Silver will always form an ion with a +1 charge. Otherwise, you will need to use clues from other parts of the ionic formulas given to decide what the charge is for the metal cation.